Hello, and welcome to another Introduction to Astronomy lecture. This is lecture number 18 on galaxies and the Milky Way. In this lecture, we will learn about how astronomers study our galaxy, the Milky Way, as well as the structure and geometry of the Milky Way. We'll also determine how you can measure the mass of a galaxy and how dark matter affects this. We'll also learn about galactic nuclei and the center of galaxies. And also, lastly, we will learn how you study galaxy evolution. It's actually quite difficult to study and map out our own galaxy because we are located inside it. It'd be really easy if we could step out a couple million light years and take a picture of our galaxy and we could see its exact structure, but we can't do that. We have to study it from inside. So the first mappings of the Milky Way were made by William Herschel and his sister Caroline Herschel. You may remember William Herschel as being the person who discovered Uranus. The two counted the two brother and sister counted stars in the Milky Way and determined that most of them lie in a flattened disk or wheel that they called it, with our solar system near the hub of this wheel. We now know today that the Herschels were right about the shape of our galaxy being a flattened disk, but they were wrong about the location of our sun and solar system due to all of the interstellar dust which obscures the views of stars that are that are beyond 6,000 light years. So today we can model our Milky Way as a vast 100,000 light year in diameter spiral galaxy that is filled with nearly 100 billion stars. 100 billion stars. That's a lot. So astronomers have to use radio and infrared wavelengths to study the most distant members of the Milky Way. And that's because we have all of that gas and dust in the way, which blocks the optical. The brightest part of our galaxy consists of a thin, circular, rotating disk of stars that's distributed nearly 100,000 light years in diameter and is about 2,000 light years thick. So we can see an artist representation of the Milky Way galaxy with its spiral arms, the Cygnus, the Perseus. We are actually in the Orion arm. And so we can see it from face on and from the side. So our galaxy is a very thin, flat disk. Again, a diameter of about 20 or of 100,000 light years, but only 2,000 light years in thickness. The youngest stars and the dense material from which they form are typically within 100 light years of this galactic plane, that plane of the disk. But the Milky Way galaxy is not uniformly distributed, and many stars are concentrated in a central bar with a series of spiral arms. So that central bar is composed primarily of old yellow-red stars, and our sun is approximately halfway from the central bar to the edge of the galactic disks. We are about 70 light years above the galactic plane as well. And since many galaxies that we see when we look out in space have the same spiral arms and central bar structure as the Milky Way, we call these galaxies barred spiral galaxies. Near the galactic center, within 10,000 light years of the center, the stars in the Milky Way aren't very well confined to that flat plane and instead form a central nuclear bulge. So, due to the limited view of visible light from all of the gas and dust, for a long time astronomers assumed that this central bulge was spherical in shape. However, recent infrared images now indicate that the bulge is more shaped like a bean. It's about 2 times wide or 2 times longer than it is wide. But the exact relationship between this elongated shape and the larger central bar is still uncertain. The galaxy itself is entirely embedded in a spherical halo of very old faint stars that are within globular clusters that extend as far as 150,000 light years from the galactic center. And within this boundary of our galaxy, there is an invisible dark matter halo, which is filled with a more mysterious and invisible mass that extends nearly 200,000 light years from the galactic center but emits no radiation. We just infer its existence based on the speeds of stars that we see orbiting in the Milky Way. The speeds that they have would not be possible without additional mass, which we don't see. And so that additional matter that we can't see, we call dark matter because it's not emitting any light. But we can tell that its effects are there. So astronomers have found that the disk has two major spiral arms that emerge from that central bar, and then several other fainter arms and also some spurs. So our sun is near the edge of a short arm called the Orion spur, which is about 10,000 light years long, and is a wisp of a major spiral arm, which contains the Cygnus Rift and the Orion Nebula. But far away from the bulge, spiral arms and these emerging spurs don't actually move in unison. Instead, each arm and spur and star in it obeys Kepler's third law, which creates a trail of material dependent on the distance from the galactic center, creating different speeds of rotation depending on what radius you are from the center. This is called differential galactic rotation. That different rotating speed, differential galactic rotation. And this explains why the Milky Way is concentrated into elongated features because differential rotation slowly stretches the galaxy out. So the mass of the Milky Way is an interesting thing to try to measure. The Sun orbits around the center of the Milky Way in a nearly circular path along the galactic disk, and it takes nearly 225 million years to complete one oscillation, one galactic year. We can use that information to estimate the mass of the galaxy itself. Given that the Sun is approximately 26,000 light years from the center, and using Kepler's third law, we find that the Milky Way up to that point has approximately 100 billion solar masses. For quite some time, it was believed that any mass outside the Sun's orbit would be negligible, since luminous stars drop off in number beyond 30,000 light years from the galactic center, which would suggest that that estimate would be fairly accurate. However, we now know with the discovery of the effects of dark matter that this assumption is very wrong. There is a lot more stuff in the Milky Way than meets the eye. So while luminous matter is quite sparse beyond 30,000 light years from the galactic center, there is a lot of invisible matter at these distances that we call dark matter. So now we'll talk about dark matter. How do astronomers observe invisible matter? Well, it's through gravitational influence, the same way that we first were observing black holes. So objects which have large semi-major axes orbit slowly, but astronomers were surprised to find that the very few luminous objects outside 30,000 light years were not necessarily moving slower than the inner objects. If all of the objects orbited the galactic center, these high-speed objects would have escaped a long time ago. They're just moving too fast to be bound by the mass contained within the center of the galaxy. The fact that they remain within our galaxy implies that there is more gravity than would be supplied by the luminous matter. In fact, there is a lot more gravity than luminous matter can account for. We actually have been able to conclude that 95% of the galaxy's mass comes from this invisible dark matter, which is virtually undetectable except by its gravitational pull. This may sound surprising. Why would astronomers believe in something that cannot be seen? But we emphasize that this conclusion is not taken lightly. Of all known celestial objects, our detection methods yield no results that could explain this gravitational effect. Currently, physicists hypothesize that this dark matter is just simply a new type of subatomic particle which we can't detect yet, much like the neutrino. So we just talked about how the center of the Milky Way didn't have enough mass to keep things bound that were in the outer parts, but it doesn't mean there's not a lot of mass concentrated in the center of the Milky Way. In fact, the center of our galaxy is home to a supermassive black hole, which we call Sagittarius A star. We actually say Sagittarius A star. That asterisk is pronounced as star in this case. So Sagittarius A star has a mass of about 4.6 million times that of our sun, and this is contained within a radius less than the diameter of the orbit of Mercury. Sagittarius A star was one of the first detected radio emissions in our galaxy, and it has since been studied in the infrared, X-ray, as well as through just by measuring gravitational effects around it. So, in the region around Sagittarius A stars, astronomers find that a 400 light year wide, 900 light year across cluster of nearby when in that region, astronomers find a pretty wide cluster of nearly 100 hot white dwarf stars, neutron stars, and other black holes, as well as thousands of other stars that are mostly older and reddish stars, with nearly 100 hot OB type stars formed within the last few million years. There's currently no good explanation on how these stars would form so close to a supermassive black hole, and perhaps they may have migrated inwards from outer parts of the galaxy. And so we can see on the image labeled 6, we can see the paths of that some of these stars in the center of our galaxy trace as they orbit around the central black hole. We can see the central black hole as being shown as the little cartoon star. And you can see how everything goes around it very sharply, like it's incredibly massive. And it is, it's 4.6 million times the mass of our sun. So when was our galaxy born, and how did it get its shape? So the age of our galaxy can be determined by categorizing the stars that are within it into two populations. We have population 1 stars. These are the bright, high luminosity stars, which are in the majority giant main sequence stars found out in the spiral arms. And then there's population 2 stars, which are the oldest. And these are like remnant stars found in the outer globular clusters of the spherical halo that surrounds our galaxy. So, from these populations, the oldest of which are 12 to 13 billion years old, astronomers hypothesize that the galactic formation process in the approximate age of our galaxy has to be at least as old as these globular clusters. So the oldest stars, those population 2 stars, are distributed in a spherical halo in globular clusters, and they're uniformly about the galactic nuclei, which suggests that if a protogalactic cloud and gas and dust gave birth to our galaxy, it would be roughly spherical. This spinning protogalactic cloud collapsed and formed a thin rotating disk, which has our population 1 stars. But the stars formed prior to the collapse and did not but the stars that formed prior to the collapse of this cloud and did not participate in it are left behind to occupy the halo. And this gives us this population distribution that we see today in our galaxy, where the young stars are in the disk and the oldest stars are in globular clusters outside. So galaxies are evolving through their own star formation and how they're using up their gas and dust to form new stars. But another way that they evolve is through interactions with other galaxies. So our Milky Way galaxy actually has quite a few smaller dwarf galaxies orbiting around it. By studying the Sagittarius dwarf galaxy, astronomers believe that the elongated shape is an indication that the Milky Way has been gravitationally tearing apart the Sagittarius dwarf galaxy, and that it will end up within our own over about 100 or 100 million years from now, along with 12 more of these other small galaxies, which are being cannibalized by our Milky Way. So galaxies kind of eat up the smaller galaxies. They're kind of merging like through a hierarchy. Smaller stuff is combining to make larger stuff. And on a grander scale, in 3 billion years, our Milky Way will actually collide with our nearest galaxy neighbor, Andromeda. These two galaxies are currently on a collision course that cannot be stopped. But one really cool thing is that when our Milky Way collides with Andromeda, despite them being so large and having so much stuff, there's actually more empty space in galaxies. And so they predict that when the two galaxies collide, that no stars will actually collide. They'll just sort of pass through each other and disrupt the gravitational orbits and the smoothness of everything, and planets may get flung out of their solar system, stars may get flung out of the galaxies, but it's very unlikely that stars themselves will crash together during the merger of our Milky Way with Andromeda. So, galaxy evolution really is quite a fascinating thing because it's not just something that affects other galaxies. Our galaxy is currently evolving, and we can see that in the future there will be another huge galactic evolution event when we collide with Andromeda. This brings us to the end of our lecture on the Milky Way and galaxies.